Homework, so if you guys got any, go ahead and fire them off. At this point, I think I've assigned up to 34. Lena. Yeah. How does this one go again? All right. The West Michigan Whitecaps are trying to maximize profits. 2 weeks ago, they found that if they sold tickets for $5 each, they're able to sell 40,000 tickets. Last week, they sold their tickets for $8. They only sold 3,000 tickets. How much should they sell tickets for in order to maximize their profits? All right. So profit is going to equal like ticket price times number of tickets sold, right? Well, I just say tickets sold. You feel okay there? Okay. So that's what my function needs to look at or look like. And let's see now. And it asks how much should they sell tickets for in order to maximize their profit. So that ticket price is going to be like my variable. Okay with that? So I need to find some kind of expression for tickets sold, right? So to do that, what I'm going to use is this information that they've given me, that when the price is equal to $5, tickets sold is equal to 4,000. And when the price is $8, tickets sold is 3,000. So what I'm interested in is how does that rate of ticket price change impact the number of tickets sold? So basically what I'm saying is that if I take 4,000 minus 3,000 divided by 5 minus 8, says that we should decrease by 1,000 tickets for every $3 we raise price, right? Is everybody okay with that? Or really, you could think about this as like 333.3 tickets decreasing per $1 change, right? Okay. So if I take this then, and I say profit is going to equal X times negative 1,000 over 3. It's not quite what I want there. Oh yeah, okay. So I have, okay. So, okay. So one other observation I'm going to make here. So the profit, when the price is $5, is just going to be 5 times 4,000, right? So 20,000. And the profit when the price is $8 is 24,000, right? So what that tells me is that that maximum certainly has to be bigger than $5. Agreed? Okay. So it's going to be 5 plus x times negative 1,000 times 3, or divided by 3, should be negative. It shouldn't. Hold on one second. I just got to get this to the numbers to work out right. One quick second. I want to look at something over here. Okay, yep, of course. Okay. All right. Okay. So the other thing that I needed to account for here, this is almost right. I just needed, at $5, we sold 4,000 tickets. And then for every price increase of $1, that should be going down by 1,000 or 333.3 tickets per dollar. So if x is equal to 0, I should get 5 times 4,000, right? Everybody agree with that? If x is equal to 3, I get 8 times 3,000, which is my other data point. So I feel good about what I've written here, right? Because this now fits the 2 data points that I've been given. There we go. So I'm just going to type this in just as it's written on my piece of paper. And then go ahead and find that maximum. So I'll set my window. The ticket price, or X, is the amount of increase in the ticket price from $5. So I don't know, probably 10 is enough. Right, 0 to 10. Probably should actually do -5 to 10, technically. Why -5? It'll come out to $0, like a $0 ticket, if X is -5. Does that feel okay, Elena? And then my Y is going to be the profit. So I know it's 24,000 at least. So my Y scale, maybe I'll make 40,000 or something. I don't really know what it's going to come out to be, but it's probably going to be not an enormous number. And then I don't know, go by 5,000 or something. Okay, let's hit graph and take a look what's going on here. All right, so there's my maximum right there. So second trace, maximum command, enter, and go over on the right side, enter, guess. So 3.49 gives me $24,083. So that tells me the ticket price, which is 5 plus X, would equal $8.50. And it told me the profit from that was $24,083 and some pennies there, 33 cents. Which is kind of disappointing, considering we already were charging $8 for a ticket to start with and making $24,000 with all that work for 83 bucks. But, you know, that's the way the cookie crumbles sometimes. Beck, certainly. Does that feel okay, Elena?
Yeah.
I stumbled through that a little bit, but I think we got the gist of it. And just as an FYI, you could have easily done, you know, like used 8 and 3,000 here. I think you would have had to consider some negatives in that case, but you could have done it with those values also and still gotten that to work. The signs on the X and the negative, and the 1,000 over 3 times X might have been reversed. I'd have to think about it for a second, but you could have done it that way also.
Thank you.
Giselle? 30? Sure. Okay. Make that a little bigger so we can all see it. All right, so I would start by factoring the denominators. I noticed that last denominator can factor just with the greatest common factor, so that x squared plus x can be x times x plus 1. So my least common denominator that I would have would just be x times x plus 1, right? So that's what I'm going to multiply both sides of my equation by. So when I do that, I have this then. Is that okay so far, Giselle?
Yeah, I think I already got it. I just didn't know the least common denominator.
Oh.
Yeah.
So I just can reduce then. And now I'm just going to multiply things out. So I get 5 and 0 when I solve the resulting quadratic. What do you notice about x equals 0, though? It's extraneous, right? That's going to give me a 0 denominator. So I just have x equals 5 as my only answer. Does that feel okay?
Yeah.
Again, if you missed factoring that x squared plus x, life becomes really difficult and rather tedious. I'm guessing that's what happened when you said you had the wrong LCD. And you can see now why getting the least is really important, because that, I'm sure, turned into like degree 4 stuff all over the place, and now you're having to like try to remember how to do that kind of stuff from Algebra 2, which was not trivial. But we shouldn't have to do it on the problems that we've cooked up. Like if you find yourself in that neck of the woods, you're probably overlooked some factoring or reducing or something. Some trick that would have been able to make it much easier. Not that it would have been wrong, just to be clear. If you had multiplied by x times x plus 1 times x squared plus x, you could still do the problem. It just, the polynomial you're left with is much more difficult to solve than the quadratic that we had. It's not wrong what you did. It just made for a much more difficult path to the end. And my life's hard enough. I don't want to take the difficult path. I want that easy road. Downhill for me all the way. Yes. Sure. No problem, Rita. Okay. So I put all this stuff in here because I wanted the directions too, because there was a lot of stuff that, oh boy, that it asked for. All right, so it says, sketch the graph, making sure to include the vertical asymptotes, horizontal asymptotes, zeros, y-intercepts. Okay, so first thing first, I would try to factor this thing. I go and I look at this and I go, oh shucks, the leading coefficients aren't 1. So the factoring is going to be a little bit more difficult. For the numerator, I want the two numbers that multiply to give me the leading coefficient times the constant term, and then add to give me that middle term. So hopefully you can see that should be -4 and 3. Once I have those two numbers, though, that's not my answer. That doesn't take me straight to my factored form. What I need to do is then replace the middle term, the -x, with -4x plus 3x. And then we'll make two groups. When I make my group, it's really critically important that there's a plus sign in between them. So if I had a subtraction symbol there, I just think about plus and negative, not a big deal. From the first group, I can take out an x as my greatest common factor. For the second group, I can take out a 1 as my greatest common factor. If I look now, there's a 3x minus 4 in common to both. So if I factor that out, I'm left with x plus 1. And then we'll have to do the other one. So I'm going to go ahead and do the same thing. So I need two things that multiply to give me -8 and add to give 7. So hopefully you see those are going to be 8 and -1. And I'm already going to write plus a negative there. So the first group, I can take out a 2x, leaving me with x plus 4. The second group, I can take out a -1, leaving me with x plus 4. The x plus 4s then are in common. When I factor those out, I have x plus 4 times 2x minus 1. Not unreasonable to have guessed and checked these, though. Like, that's the process that we use to factor these, because that constant term at the end and the leading coefficient were very small numbers. It wouldn't have been difficult to just, okay, I know the leading coefficient for one of these has to be a 3, the other one has to be a 2. There's only a couple of things that are going to multiply to give me -4. I can just kind of like guess and check with what has to be there. There's only like 4 things you'd have to check, so you could have done it that way also, but that's the method. Once I have that, I see that I'm going to have vertical asymptotes where the denominator is equal to 0, so -4, and then +1/2. I'm going to have x-intercepts, or zeros, where the numerator is equal to 0, so that's +4/3 and then -1. My horizontal asymptote, well, this has horizontal asymptote because the degrees of the numerator and denominator are the same. They're both degree 2. So I know the horizontal asymptote is just going to be leading coefficient of the numerator over leading coefficient of the denominator. And then the y-intercept, I'm just plugging 0 in for x, so everything except for the constant terms just drop out. -4 over -4 is +1. So that's the key points there. So far, so good, Rita? I like zoomed through that. Are you?
Yeah.
That's okay. All right. So we'll go ahead and try to sketch a picture in here then. So 1, 2, 3, 4. There's one asymptote. And then 1, so a half is in here. Boy, these grid lines are real tight together. That's all right. Then I have my x-intercept, so -1, 0, and then 4/3 is 0 is like over here somewhere. Then I have 0, 1, and then I have y equals 1.5. So let's go ahead and figure out what's happening at these asymptotes. Clear that out of there. Alpha y equals. So we have 3x squared minus x minus 4 over 2x squared plus 7x minus 4. Vars, y vars, function, y1. So I need to figure out what's happening on the left side of -4. So I'm going to pick some numbers that are a little bit smaller than -4, but are getting progressively closer to -4. Oops. So -4.1, -4.01, and -4.001. And I see that they're getting bigger each time. So I know that I must have something like that over there. Now let's check what's happening on the other side. So I'll start from the right side of -4, so something a little bit bigger than -4, and then progressively get closer and closer. And at this point, I'm pretty sure that it's pointing down. So I can see that I'm going to come up like this. I got to go through those two. And then let's see what's happening on the other side, or the left side of -1/2. So we'll start at -0.51, and then we'll go to it's positive, excuse me, right? It's positive 1/2 is our asymptote. So the left side is 0.49, and then 99, and then 9999. That's no, no, no in German. So I guess I see that it's doing this. Now, observe that crossed the horizontal asymptote. That's not a big deal if it's happening in the middle. It's just not going to cross at the ends. And then from here, I can tell, okay, well, the last one, I don't need to really use my calculator because I got to go through that x-intercept. So that has to be starting down and then going through that x-intercept and following. So that one I got for free. Does that feel okay?
Yeah.
Yeah, the factoring was probably a little hazy. Yeah. Again, you could have set them equal to 0 and just used the quadratic formula. And that would have given you your vertical asymptotes, and it would have given you your x-intercepts. And if any of them matched, you'd have known there's a removable there. But no problem. Last call on this stuff. Okay. Oh, excuse me. All right, so let's do 14.3 then. Here we're going to be looking at solving inequalities. God bless you. And here I'm just going to go through and kind of run through some examples, and we're just going to kind of do this that way. So we're going to start with just a normal old quadratic example. So the more complicated your polynomial is, the more difficult kind of these solving an inequality is. If this is a linear inequality, there's not much to it. It's not really any different than a linear equation. If it's a quadratic inequality, though, this becomes a little more complicated. So really, once you get any polynomial that's bigger than degree 1, this is kind of the process that I'd want to follow. So what we'll do is we'll just start by setting it equal to 0, just pretending it's an equation. And then I'm going to solve this equation. So you could factor this, or you could add 4 to both sides and then square root it, or whatever. Use the quadratic formula, I guess, if you wanted to. Any of those things would be fine for this situation. So these are the two places where the graph can change from positive to negative, right? Since I know that this function is a polynomial, it's continuous, the only way to change from positive to negative is when it crosses the x-axis, when it hits 0. Everybody's okay with that idea? So what I'm going to do now is I'm going to draw something called a sign diagram. And I'm going to list those two places where I know the graph changes from positive to negative. And now what I'm going to do is I'm going to indicate whether the -2 and +2 should be included in my solution set. Since this says greater than or equal to 0, should 2 and -2 be included? No, because that's where the function is equal to 0 at. So I'm going to put an open circle there, just like when we graphed inequalities way back in like pre-algebra, to indicate that that value is not included. Everybody's good so far? And then I'm going to pick some test values. So I'm going to pick a value between -∞ and -2. It doesn't really matter what it is. I'm going to choose -3. Then I'm going to pick a test value between -2 and +2. Doesn't really matter what it is. I'm going to pick 0. And then I pick a test value between 2 and +∞. I'll pick 3. It doesn't really matter what it is, though. So far, so good. I'm going to now plug those in to the function part and see what I get. In fact, I don't even really care what I get. I just really care whether it's positive or negative. So if I do -3 squared minus 4, I get positive number, right? I get 5, but who cares what it is? I just care that it's positive. If I do 0 squared minus 4, what do I get? A negative. It's -4, but I don't really care that it's -4. I just care that it's negative. If I do 3 squared minus 4, I get positive. So since I have greater than or equal to 0, I care about this section and this section. So my answer would be anything from -∞ to -2, or anything from +2 to +∞. Now, some of you might have said, well, like, shoot, Mr. Kulik, like, I know the thing looks like this, so, like, those are my answers, right? I don't really need to do all that work. And I'd say, sure. What happens if that's a more complicated polynomial, though? This is just me demonstrating a concept. Surely, yes, you could have thought about this graphically and come up with the same answer without having to do any of the work that I just did, and that's fine. But when things get more complicated, it's less likely you're going to be able to just picture what the quadratic looks like or what the function looks like when it starts becoming, degree 3, or it becomes rational. It's much more difficult to imagine what these things look like just in our head. And I'm just kind of proving a concept for us right now. But I want to acknowledge that, yes, in this case, this one would have been perfectly reasonable to have mental mathed it. That's not a difficult proposition. Okay, let's do another example. So here's another polynomial, but this time it's a little bit more complicated because it's a degree 3. My process, though, is not going to change. Just like I did before. I'm going to start by just setting it equal to 0. I notice I can take a greatest common factor of x out. And then I notice the quadratic x squared minus 4x plus 4 factors to x minus 2 times x minus 2. So I end up with, again, 2 zeros at 0 and 2. I'm going to draw my sign diagram. Now this time, should 0 and 2 be included in my solution set? Yes, because it's an or equal to. So this time I'm going to put a filled circle in there to remind myself that those are a member of my solution set. And I'm going to do the same thing I did before. I'm just going to pick some values. So I'll pick -1 for something less than 0, +1 for something between 0 and 2, and 3 for something bigger than 2. Now the place where I'm going to imagine plugging them in is right here. So if I plug -1 in, I have a negative times a negative times a negative. 3 negatives is negative. Everybody's okay with that rationale? That's where I find it easiest. I don't really care what the number is. I just care about the sign. In the factored form, plugging in, it's all I have to do for mental math is some whole number adding and subtracting, which I'll take that. Especially when I don't even need to remember what the number was. I just cared about the sign. When I plug +1 in, I get positive times negative, bless you. So that should be positive. And when I plug 3 in, I get positive times positive times positive. So that should be positive. Everybody's cool with how I filled the sign diagram in there? Okay. Since I have less than or equal to 0, what part gives me my solution? Less than or equal to 0? The negative part, right? So I want here and something else. 2, right? Because that is equal to 0 also. And now you should say to yourself, Mr. Kulik, how do I write that? Well, you start the same way. So you do negative infinity to 0. Notice I'm using the bracket there because 0 is included. And then union, I also need to include the single number 2. 2 isn't an interval, so I just use the regular old set notation with the squiggly brackets. Oh, gee willikers, Mr. Kulik, that was sneaky. I would have forgotten about 2. I know it's sneaky, but it's not. Once I've shown you the trick, it's a lot less sneaky the second time around when it's aha, I need to be careful about those. Keep in mind that can only happen in a or equal to situation, right? So let's do another one. How's this going so far? Everybody okay? Not too big of a deal, right? It's kind of a nice, neat process where you can kind of see, okay, there's some stuff to watch out for, but it's still basically the same procedure. What if I give you a rational function now? So I know the zeros are going to come from setting the numerator equal to 0, right? But a rational function is not continuous, right? Or doesn't have to be continuous anyways. You could have a discontinuity at any place where the denominator is equal to 0. And not only can a function change sign at a 0 where it crosses the x-axis, it could change sign at a discontinuity, right? You've seen it, a discontinuity where one end of it is positive and then the other end is negative, right? You've seen the discontinuity do that. So we also have to worry about those discontinuities. Those have to appear in our sign diagram also. All right. Now let's fill in whether these should be open or closed. Should x equals 4 should that be open or closed? Closed. Why? Great. Should -1 be open or closed? Always open. Why? Because a discontinuity is not part of the domain. Any discontinuity, regardless of whether it's an or equal to or not, is going to be an open circle because discontinuities are like an asymptote. There's no value there, right? Those will always be open. Everybody good so far? Now it's the same thing. So -2, I'll pick a 0 and then say a 5. So if I plug -2 in, I get negative over negative. That's positive. When I plug 0 in, I get negative over positive. That's negative. When I plug 5 in, that's positive over positive. That's positive. Everybody feel okay? Good. So if we want the parts that are greater than or equal to 0, which parts do I want? The positive parts. So I want those. So I'll write -infinity to -1. That one gets a parenthesis. And then I'll write 4 to positive infinity, but the 4 gets a bracket. What do you say? So far, so good? Still doing all right? Not too bad, right? It's like, it's a little different. We didn't really do this in Algebra 2, but like, it's not that bad. And those of you planning on taking calculus next year, we do this kind of sign diagram testing a fair bit because there's lots of stuff that we care about when things change from positive to negative. So this is a technique that will translate. Okay. Ooh, Mr. Kulik, this is weird. All right, well, we'll start the same way. Start with the zeros. So that's just going to be the numerator set equal to 0. So I can square both sides. And then I get just -4. Everybody's okay with that? Okay. Discontinuities. So we can solve or set the denominator equal to 0. Now notice that, how do we solve a absolute value equation? You do that, but then you also have to negate what it's equal to. Now in the case of 0, it doesn't really matter because positive 0, negative 0 is the same value. We just get x equals 1. But there's one other, well, I guess it doesn't really matter. It's fine. This is good. Not going to worry about it right now. We'll just let it come up naturally. So I have -4 and a 1. Should I be using, for the -4, open or closed? Open, because it's a strict inequality, strict greater than. And the 1 is, oh my goodness. The 1 is open also because it's a discontinuity. That'll always be open. Okay. So we pick a values for our test values. So I pick -5, 0, and 2. Again, there's nothing magic about the numbers I'm picking. I'm just trying to pick stuff that's convenient. Could you pick like -7,342 instead of -5? Well, sure, but like, why would you? If I plug -5 in the numerator, I get imaginary. So instead of writing positive or negative here, I'm just going to write no real solutions. So that's not going to be part of any answer, regardless of whether it was positive or negative, because it's a non-real thing, so it just doesn't even count. Everybody's all good with that? Okay. If I plug 0 in, I get positive over, what's the absolute value of 0 minus 1? Positive. So positive over positive is positive. And if I plug 2 in, I get positive over positive, so that's positive. Okay? So if I write my answer now, I would say from, what would I say for my answer here? Right, I have greater than 0. Well, you just use a parenthesis. So good. Starts at -4 with a parenthesis. I agree with that. Good. Good. Yeah, so you do need 2 separate intervals. The temptation here is to try to make that one thing, but we have that discontinuity at 1, so you can't just write that -4 to positive infinity. Christian.
Is -1 a discontinuity?
Is -1 a discontinuity?
Yeah. Oh, I know.
That gives you -2.
Yeah.
So it's okay. That's okay. Fair question to ask. What do you guys think? Think you got it? It's not too bad, right? It's kind of like a fun little process. I like it because it's visual, right? Like that makes life a lot easier for me. I'm a visual guy. That always helped me. So this was the last thing in chapter 14, although I am going to do an additional chapter 14 topic. So we're going to do one more, and then we'll do worry about the test. You guys should be planning on a homework quiz, though, pretty soon. I would not expect to have to worry about topics past, say, the solving. So don't worry about anything we just did today. If you're good up through solving, I think you'll be fine for the homework quiz. So we're going to stop here. Next time we're going to do partial fraction decomposition. which is just a mouthful, as well as the homework quiz. And then on Friday, we'll kind of talk about the test format and do our test review, and then we'll do the test next week. Sound okay, Rita?
Did you say that supplementary?
No, this is inequalities. So this solving equations, I think, is fair, but not up, up through whatever 34 or something in the homework.
Yeah.
Sound good? So that was not too bad, right? We have 40 minutes to try to get some stuff done.